We're going to take a look at our homework from last night, worksheet number 3 on work. And we want to go over four questions, number 4, 5, 6, and 7, starting with number 4. Number 4 says a 1.30 times 10 to the 3 kilogram car begins at rest and accelerates to a speed of 60 kilometers per hour over a distance of 200 meters. How much work is done? How much work is done on the car? Clearly a work question since we're asked for work here. How do we go about this? Well, let's convert this speed to meters per second first, and let's write down the rest of our givens as well. We know that the mass is 1.30 times 10 to the 3 kilograms. We know that VI, it starts at rest, so VI would be 0 meters per second. VF is 60 kilometers per hour, but we're going to convert that to meters per second. I don't have the value for that. What is that in meters per second? 16.6 repeating. Thank you. And what else we got here? The distance or displacement of 200 meters. And we want to find the amount of work done here. What do you want to say here? Presumably, it appears at least as if the force is in the same direction as the displacement. So we're allowed to use W is equal to F times D without tacking on the cos theta. You guys know that we can always tack on the cos theta if we want, but if it ends up being the situation that the force is in the same direction as the displacement, we know that the angle is 0 and cos 0 is 1. So it means the equation becomes F times D. But a little bit of a problem here. I don't know what F is. We could, go ahead. Okay, yeah, so we could do this. We could say F is equal to M times, we have displacement, right? We could say F is equal to M times A, but then we don't have A. But we could find A using VF squared is equal to VI squared plus 2AD. So solve for A using that equation, then solve for F using M times A, and then solve for W using F times D, and that'll work. But I think that's a little bit more roundabout way of doing it than the way that Bruce just suggested, which was the other equation for work, which is really the definition for work, right? Work is defined as a change in energy. So let's set it equal to the change in energy. And then let's say, well, the final energy is kinetic energy. So we're going to say 1/2 mvf squared minus 0, because that's what it starts with, right? It's 0. So delta anything is anything final minus anything initial. In this case, delta E is E final minus E initial. Kinetic energy is final, and there is no energy in the beginning. So it just becomes a W is equal to 1/2 mv squared. Don't just say, oh, next time I have a problem, let's just say, oh, the work is one kinetic energy. No, it's not always just kinetic energy, right? It's always final minus initial energy. Okay, that's not always equal to the kinetic energy at the end, because sometimes there's an initial or whatever. So don't just automatically do that. Think about each question and make sure that that's the case here. We got 1.30 times 10 to the 3 kilograms times VF 16.6667 squared. And when we do that, it should work out to be 1.81 times 10 to the 5. How many people did it my way right here? Okay, how many people did it W is equal to F times D, and then F is equal to M times A, and then A is equal to, or VF squared is equal to VI squared plus 2AD? Yeah? Hey, did you get the right answer? Yeah. Go figure, you end up getting the same answer, right? Two legitimate ways of solving a problem, and coincidence that you got the same answer? Of course not. You have to. So don't panic about thinking the way that I think. Just make sure you think. Okay, number 5. 5 says a 1.30 times 10 to the 3 kilogram car begins at rest and accelerates to a speed over a distance of 60 kilometers per hour over a distance of 200 meters. What's the net force acting on it? This is the same question, except that we're looking for the force. We just solved for the work. It's 1.81 times 10 to the 5 joules. If we know the displacement, it's all we need to solve for the force. Now I can say W is equal to F times d. Now, the one benefit of doing it the way that Danny did it, right? W is equal to F times D, the last question that is, and then say, oh, F is equal to M times A. Oh, wait, we need to find A using VF squared is equal to VI squared plus 2AD. It's more work for question number 4, but when you get to question number 5, you already have the answer, right? So you spend more time solving question 4, but less time solving question 5. I think that W is equal to delta E is still quicker, even after we do question number 5, but it's not as much quicker as it seemed in the beginning here. We're solving for F, so that's going to be W over D. W is 1.81 times 10 to the 5, divided by the displacement of 200 joules, and that's equal to 903 newtons. Six. There's a 0.43 kilogram ball traveling at 130 kilometers per hour, hits a wall and comes to a rapid stop. Squishing itself 2.3 centimeters. What's the force of the wall acting on the ball in order to stop it? And then what's the force of the ball acting on the wall? I think we're going to solve this using work, although it's not the only way we could do this. Again, F is equal to M times A. A, maybe you could solve for that using VF squared is equal to VI squared plus 2AD, but I think I'm going to use work here. W is equal to delta E equals final minus initial energy. Okay, let's say 0, how much energy did it have to begin with? No, it was moving at 130 kilometers per hour, right? Right? So let's say it becomes negative 1/2 of what, 0.430 times VF. 130 kilometers per hour in meters per second is what? 444? What is it? 36.11? All right. Let's try that again. And when we do that, we should get, I believe, negative 1.22 times 10 to the, oh, sorry, that's work, right? That gives us the work in joules, which we can in turn set equal to F times D. So whatever we get for the work there, just rearrange that to solve for F, or plug it into the work equation to solve for F. And when we do that, we should get negative 1.22 times 10 to the 4. Displacement here, delta D. Some people are probably thinking, oh, it's squishing the ball. Isn't that displacement X? Right? How much it's squished? Yeah, it actually is. But understand that during the time the ball squishes, the ball is traveling, right? So it's actually both X and delta D in this case. Does that make sense? It's not always the case. If I throw this pen across the room, then the displacement is delta D, not X. But if the ball is moving towards something, towards a wall, and squishes, it continues to move as it squishes. So if it squishes 2.3 centimeters, then it must move 2.3 centimeters in that time as well. So yeah, it could be X, but yeah, it could be displacement delta D as well. There's my first force. Now, what's my second force? It's positive, right? If object A applies a force on object B applies an equal and opposite force on object A. And finally, question number 7. It says a 2 kilogram box slides down a 1.5 meter high hill at a constant speed of 4 meters per second. What's the net force acting on the ball? How much work does friction do on the box as it slides down the hill? And if the distance covered by the box is 4.6 meters, what is the force of friction? And what type of energy changes in this problem? What type of energy does not change in this problem? Holy cow, there's a lot to this, eh? Good thing somebody asked me to go over this one. Oh yeah, let's answer the first one first. It goes at a constant speed of 4 meters per second. It's in a state of, what do we call that when something's moving at a constant speed? It's in a state of, 2 words. Yeah, something equilibrium, translational equilibrium. And what do we know about an object that's in translational equilibrium? The forces are balanced. There may be forces, in fact, there are clearly forces acting on this, but the forces are going to be balanced. And if the forces are balanced, what does that tell us about the net force? Zero. All right, it doesn't mean the force is zero, it means the net force is zero. Now, how much work does friction do on the box as it slides down the hill? Well, we'd want to say the work done by friction, we'll call that question B, is F times D. Do we use a force of 0 newtons here? No, because friction isn't 0 newtons, is it? How much, what's the force of friction? We don't know it, do we? Can we find it? Sure we can. Sure we can. Here's a 2 kilogram box. We know that the net force is 0, which means oh, we don't have the angle, do we? No, we don't. We can't do it that way. What was I gonna do here? I was gonna find F parallel, and F parallel would have to be equal to the force of friction then. All right. That's not gonna work for me because I don't know what the angle is. Is that okay that I was starting to do it that way? Sure. It's a thought that I had, right? I thought that's what was gonna lead me to the answer. Um, don't sweat it if you go down the wrong path and you have to come back, right? I didn't get a wrong answer, did I? Then it's all good, right? So what are we going to do? Jonah, what do you suggest I do? I'm sorry? Could we find theta? Um, we don't. Oh, yeah. Okay. 4.6 meters, 1.5 meter high hill. Um, we got to be careful with that because it doesn't say that it slides all the way down the hill, right? If the distance covered by the box is 4.6 meters, but it doesn't say that the length of the hill is 4.6 meters. I think we probably mean that, but I can't remember, to be honest, when I wrote the question if I did or not. So we're going to be careful with that one, okay? Um, you know what though? No, you can do that because the only other way we can do it, the way that I was thinking, or at least the second way that I was thinking, is to say W is equal to delta E, and I would say delta E would be zero final energy minus initial energy, mgh, right? And we're assuming that it's going all the way down the hill in this case. So Jonah, we could, in fact, do exactly what you suggested there. Find the angle using how far it goes and the height of the hill, and then find F parallel, and then find the force of friction. Yeah, that would work because we're making the same assumption that I was questioning with yours. We're making the same assumption in what I'm doing here right now, and that is that it's going all the way down the hill. So yeah, it would work. Although to be honest, I think this way is going to be a little bit quicker here. Now there is kinetic energy as well, right? But it's constant speed, right? Kinetic energy is not changing, so let's not even include it if it's not changing here. Let's say W is equal to 0 minus, what do we got? 2 times 9.81 times the initial height of 1.5. And that gives me, I think, 29.4. Negative 29.43 joules, or negative 29.4 joules. How much work does friction do on the box as it slides down the hill? Negative 29.4 joules because it lost that energy due to friction. What's the force of friction? All right. Well, now I got to go back and find the force. I could do it Jonah's way. In fact, if we had done this question Jonah's way, we'd already have the force of friction, right? Since I didn't do it that way, now I'm going to go back and say W is equal to F times D. F is equal to W that we just found over displacement. This displacement would be 4.6, not the 1.5. And that gives us a force of 6.40 newtons. Yeah, 6.40 newtons. What type of energy changes in this problem? Gravitational potential. What kind doesn't change? Kinetic, because the constant speed, right? 4 meters per second. We didn't even use that number for speed, right? It doesn't matter how fast it's moving. As long as it's not changing speed, the forces are going to be the same. That's a tough question. That's a tough one. How many people got that? Not many, eh? Jonah, you had the right idea there. Did you just kind of figure that out today, this morning? Okay. Um, you would have gotten the same thing, right? Because as I said, um, I ended up making the same assumption that you did in order to solve this. I just did it in a different way, but it would have ended up giving us the same answer.